Assalamualaikum warahmatullahi wabarakatuh and good morning. My name is Wan Yasmin Zulaika binti Wan Kamarul Azrisham and my matrix number is 03DKA25F1095. Today I want to present about soil consolidation. Soil consolidation is a natural process that occurs when external loads or pressure are applied to soil, causing it to compress and reduce in volume. This phenomenon has significant implications for civil engineering and construction because it can impact the stability and durability of structure built on top of the soil. A thorough understanding of soil consolidation is crucial if you work in the geotechnical industry, as it can affect the behavior of soil and the performance of structure. Accurately measuring and predicting soil consolidation is essential to ensure safe and sustainable infrastructure development. There are various methods to monitor and address the soil consolidation, making it possible to mitigate its effect and design structures that are durable and stable. The principle of soil consolidation is based on the effective stress concept introduced by Carl Tzewski. In soil mechanics, the total stress in a soil mass is divided into two components, which are effective stress and pore water pressure. This relationship can be expressed using the equation sigma equals sigma prime plus U. When an external load is applied to saturated soil, the pore water pressure increases initially because the water in the soil voids carries most of the loads at the early stage. At this point, there is little immediate compression of the soil structure. Over time, water gradually drains out from the soil voids. As drainage occurs, the excess pore water pressure decreases progressively. As the pore water pressure reduces, the applied load is transferred from the water to the soil skeleton, increasing the effective stress. This increase in effective stress causes soil particles to move close together, resulting in a reduction in volume and eventually loading to settlement. Overall, this process occurs gradually over time and is highly dependent on soil permeability, with clay soils experiencing much slower consolidation compared to more permeable soil. The concept of soil consolidation refers to the gradual reduction in soil volume due to the expulsion of water from the soil voids when subjected to an external load. This process is particularly significant in saturated fine-grained soils such as clay, where permeability is low and drainage occurs slowly. Soil consolidation is generally divided into two main stages. The first stage is known as primary consolidation, which occurs the excess pore water pressure is dissipated as water slowly flows out of the soil. This stage is responsible for the major portion of soil settlement. The second stage is secondary consolidation, also known as creep, which takes place after primary consolidation is completed. During this stage, settlement continues due to the gradual adjustment and rearrangement of soil particles, even though pore water pressure has largely dissipated. Both stages contribute to the total settlement of the soil, which must be considered in geotechnical design to ensure the stability and safety of structure. In this section, I will explain in detail the construction process and site work method for soil consolidation, which is a ground improvement technique commonly used in soft soil areas to increase soil strength and reduce long-term sediment. To begin with, the first step is site clearing. This process involves removing all vegetation, organic matter, debris, and any unsuitable surface materials from the construction area. The purpose of site clearing is to ensure that the ground surface is clean, uniform, and suitable for further geotechnical works. A properly cleared site also helps in achieving accurate soil investigation results. The second step is soil investigation. At this stage, various geotechnical tests are carried out, such as borehole drilling, standard penetration tests, or other in situ testing methods. These tests are used to determine the soil profile, shear strength, compressibility, permeability, and groundwater conditions. The collected data is very important because it will be used to design the soil improvement system, including the spacing and depth of vertical drains as well as the required surface load. After the soil properties are confirmed, the next step is the installation of prefabricated vertical drains or PVD. PVDs are synthetic drainage materials installed vertically into soft soil layers using a mud drill. Their main function is to shorten the drainage path of pore water within the soil. Normally, in natural conditions, water drains very slowly in clayey soils due to low permeability. However, the PVD installed, excess pore water can move horizontally towards the drain and then flow vertically out of the soil layer. This significantly accelerates the consolidation process. Once the PVD installation is completed, the next stage is the application of surcharge loading. Surcharge is an additional temporary load placed on top of the ground surface, usually in the form of soil fill or sand fill. The purpose of this loading is to increase the effective stress within the soil. As the load is applied, the pore water pressure increases initially and then gradually dissipates as water flows out through the vertical drains. This process causes the soil particles to rearrange and become more compact, resulting in ground settlement before actual construction begins. This is important to ensure that most settlement occurs during the pre-loading stage rather than after the structure is built. During and after loading, settlement monitoring is continuously carried out. Instruments such as settlement plates, magnetic extensometers, and piezometers are installed to measure vertical ground movement and pore water pressure change. Settlement plates are used to observe the amount of ground surface settlement over time, while piezometers measure the reduction of pore water pressure within the soil layer. The monitoring data is recorded regularly to evaluate the rate of consolidation and to determine whether the soil has reached the required level of stability. In addition, field observation is important to ensure that the surcharge load is applied evenly and that there are no signs of excessive differential settlement or instability. If any abnormal readings are detected, corrective measures will be taken immediately to maintain safety and design requirements. Once the required settlement is achieved and the rate of consolidation becomes very low, the surcharge load may be removed gradually. At this stage, soil is considered significantly improved with increased strength and reduced compressibility. This allows safe construction of the main structure such as roads, embankments, or building on top of the improved ground. Finally, all monitoring data and field results are analyzed and documented. This analysis is used to confirm that the soil consolidation process has achieved its design and objective, including the target degree of consolidation and allowable settlement limits. In conclusion, the soil consolidation method using prefabricated vertical drains and surcharge loading is very effective ground improvement technique. It helps to accelerate natural consolidation, improve soil stability, and significantly reduce the risk of long-term settlement, ensuring the safety and durability of future construction projects.
Assalamualaikum, my name is Nadamia Arisha binti Muhammad Yusof, and in this section I will explain the key terms in consolidation analysis and also how the calculations work. Consolidation is very important in civil engineering because it helps us predict how soil will settle under a load, which is critical for a safe foundation design. Number 1, we have volume compressibility. Volume compressibility, or MV, describes how much soil decreases in volume when pressure is applied. It shows the compressibility of soil per unit increases in stress. A high MV means soft clay that compresses a lot, while a low MV means stiff soil like dense sand, which hardly compresses. To calculate MV, we look at the change in soil's void ratio from lab tests. Compare it with the initial void ratio and relate it to the stress increase applied to the soil. In simple terms, we are asking for this amount of pressure, how much will the soil shrink? Number 2, we have coefficient of consolidation. The coefficient of consolidation, which is CV, indicates how fast the consolidation process happens. It depends on the soil's permeability and compressibility and is usually expressed in meter square per year or meter square per second. To find CV, we consider the soil properties, drainage path, and time. Number 3, we have degree of consolidation. Degree of consolidation, also known as U, shows how much consolidation has already occurred at a certain time, expressed as a percentage. 0% means no consolidation has occurred, while 100% means the soil is fully consolidated. We compare the settlement that has happened so far with the total expected settlement. For example, if half of the settlement has occurred, the degree of consolidation is 50%. Next, we have time factor, also known as TV, is a dimensionless value used to calculate consolidation over time. It connects time, soil thickness, and coefficient of consolidation. We use TV to relate how long the load has been applied to how much settlement has occurred. It is basically a way of measuring the progress of consolidation at any given time. Next, we have the rate of settlement. The rate of settlement refers to how quickly the ground sinks under a load. Depends on soil type. For example, clay is slow and sand is fast, and drainage conditions. We observe the soil properties and drainage, then estimate how fast the settlement occurs over time. This is important for planning construction design. Next, we have consolidation settlement. Total consolidation settlement, denoted as SC, is the total amount of settlement that will occur after the soil has fully consolidated. It depends on three main factors, which is the soil's compressibility, which shows how easily the soil can be compressed under stress. Number 2, the increase in stress applied to the soil, for example, from a building or pavement. Number 3, the thickness of the compressible soil layer. Thicker and softer soil results in larger settlement. In calculation, this is the final value we compare with the allowable settlement in design. In simple terms, SC shows how much the ground will eventually sink after fully consolidated. Lastly, we have the settlement at time, which is the settlement at a specific time, denoted as ST. Is the actual amount of settlement that has occurred at a particular time before full consolidation is completed. In calculation, we take SC and multiply it by U, the degree of consolidation at that time. Early on, settlement is small because only part of the consolidation has occurred. Over time, settlement approaches the total value, also known as SC. This is used to predict how much settlement has occurred during the construction or service. In simple terms, ST shows how much the ground has actually sunk at the given time. Thank you.
My name is Nur Nasira binti Nurisan. My metric number is F1013. I will explain the problem related to consolidation. General definition of consolidation. Soil. Consolidation is the process of reduction the volume of soil due to the release of water from soil pores when subjected to a load. Okay, the first point is excessive settlement. Occurs when soil experiences a continual reduction in volume. Other than that, can affect the stability of structures such as building and roots. And number 2 points is differential settlement. Occurs when settlement rates are different in different areas. And then can causes crack in foundation, wall and floors. And then can lead to structure tilting or failure. So, problem of consolidation will be time dependent process, which is consolidation occurs slowly, especially for clays, and their deposition can continue even after construction is complete. And the last is difficult to predict in the long term. Okay, this slide also have the picture. We can see the house be cracked at the wall. So consolidation is important for the construction, buildings or anything construction. So I will continue the problem, which is cannot be important to consolidation, which is the difficulties in analysis and design, which is require accurate soil parameters such as compression index and reinforcement coefficient. And then estimation errors can increase repair costs. Number 2 is reduction in shear strength, which is during consolidation, the soil may experience a reduction in shear strength, and then causes risk of slope or foundation failure. The last one is critical for soft soil, which is soft clays. And then the risk of structure failure, if not taken into account in design, can cause serious damage, affect user safety and structure durability. And the last one is drainage problems, which is inadequate drainage system slow down air circulation, causes consolidation to take longer and will affect soil performance. Okay. In conclusion, soil consolidation is fundamental concept in geotechnical engineering that significantly influences the behavior and performance of soil under applied loads. It refers to the gradual reduction in soil volume due to the expulsion of pore water from the voids, particularly in fine-grained soils such as clay. This process is highly time-dependent and can continue over an extended period even after the completion of construction. The effect of consolidation, especially excessive and differential settlement, poses risks to the stability and integrity of engineering structure. If not properly addressed, this issue may lead to structure damage, serviceability problem, and increased maintenance costs. Furthermore, factors such as low permeability, excess pore water pressure, and secondary consolidation further complicate the prediction and control of settlement behavior. Therefore, it is essential for engineering to conduct thorough site investigation and laboratory testing to accurately determine soil properties and consolidation parameters. The implementation of appropriate ground improvement techniques such as preloading, vertical drains, and soil stabilization is crucial in minimizing the adverse effect of consolidation. Ultimately, a comprehensive understanding of soil consolidation enables of engineering to design safer, more stable and durability structure, ensuring long-term performance and sustainability in construction projects.